Alright, so here we have system of equations and a little bit of modeling. They are related. When we say modeling, we're not really talking about runway modeling or magazine modeling. It's very similar, almost just as lucrative and glorifying, but it's math modeling. So you can run 0.2 kilometers every minute, and a horse can run 0.5 kilometers every minute, but it takes 6 minutes to saddle a horse before it can start running. First, we want to define some variables. So you pick what you want. If you want distance to be d, as in dog, or distance, and time to be t, as in Tom, or time, then you can use those. If you want to just use x and y, then use x and y. It doesn't really matter. It's up to you, but you want to make a conscious decision and define the variables. So I'm going to say that distance is d, and that time is t. I used a lowercase d and a capital T because when I'm writing numbers and variables, my sloppy handwriting, it's easier for me to distinguish a lowercase d from than a capital D, because a capital D could start to look like some numbers, and same with capital T is easier to distinguish than lowercase t because lowercase t can look like a plus sign sometimes. That's why sometimes it's better to stick with x and y. It's up to you though again. Or keep in mind that when we use the word variable, it can actually be a word. You could just use distance, or you can use time. That's fine as well. Okay, next thing. I want you to write an equation to represent the distance you traveled with respect to time using your variables. So go ahead and do that. Okay, so for the variables that I chose, I have d equals 0.2 times t. That's an equation that represents the distance that I traveled with respect to the time. Keep in mind, remember, in general, and this is something that comes up a lot in relationships and word problems and modeling and math, is distance equals rate times time. And that's what we have here. Distance equals 0.2 kilometers per minute is a rate, and t is a time in minutes. D is a distance in kilometers. Alright, so now I want you to create an equation to represent the distance the horse has traveled with respect to the time using your variables. Also keep in mind that the horse didn't start running until 6 minutes after you did. So that's going to come into play in your equation. So pause the video, write down your equation, unpause when you're ready to discuss. Okay, so your equation for the horse with respect to time should be d equals 0.5 t minus 3. Again, your variables might be different, that's okay. How do I come up with the minus 3 though? Well, here we have to use the knowledge that the horse started 6 minutes after we started. So what does that mean? Well, I know that I have my generic equation d equals 0.5 t, and then plus or minus, in this case, some other variable, or some factor. How do I find out what that is? Well, I know that the horse has traveled a distance of 0 kilometers when the time is 6 minutes. So I plug in that point, which graphically is going to be an x-intercept because the y value is 0. So I plug in that point to find this other factor for my equation. So if I do 0.5 times 6, that's going to be 3. I subtract 3, so I get x equals negative 3. So my equation for the horse is d equals 0.5 t minus 3. My equation for me is d equals 0.2 t. I don't have plus or minus anything here because I'm starting to run when the time is 0. Okay, so the next question is, assuming you and the horse are running along the same path, does the horse ever catch you? If so, when? If not, why not? Well, how can we figure out if the horse would catch us? Very good. We'd solve the system of equations. We have a system of two linear equations, two unknowns. So we can solve that system. So we have d equals 0.2 t, and we have d equals 0.5 t minus 3. So now how can we solve this system of equations? Well, you may remember from a previous algebra class, you could do substitution or elimination. Either one works. In this case, the system is set up very nicely to do substitution. So that's what I'm going to do. So what do we mean by substitution? Well, I can see that both of these equations equal d, or have d isolated on one side, so therefore I can set them equal to each other, and I can say 0.2t equals 0.5 t minus 3, and now solve for t. So if I subtract 0.5, 0.2 minus 0.5 is going to be negative 0.3, t equals negative 3. And then from here we can divide by negative 0.3. And so we end up with t equals 10 minutes. So, assuming you and the horse are running along the same path, does the horse ever catch you? Yes, the horse does catch us, because we got an answer. So, say when we tried to solve this system, we never got a solution, then the horse would not catch us. So in this case, we can answer the question in the context of the problem. So yes, the horse catches us in 10 minutes. Alright, so now I want you to graph your two equations on the coordinate plane. So go ahead and do that, and then at the same time, once you're finished doing that, you can answer the question, why are we only looking at the graphs in quadrant 1? So graph your two lines and answer the question, why are we only looking at the graphs in quadrant 1? Pause the video, unpause when you are ready to discuss. Alright, so our graphs should look like this, where the red, this is me, green is the horse, and I know that I start at the point 0, 0, because remember my equation was d equals 0.2 t, and so from there I go up 1 over 5, up 1 over 5, and the horse starts at the point 6, 0, because the horse had the equation d equals 0.5 t minus 3, and the horse goes up 1 over 2, up 1 over 2. We can see our intersection point. We know the x-axis represents t and the y-axis represents d. So this is what our graph should look like. So now, why do we only care about quadrant 1? Well, we only care about quadrant 1 because our two variables, t and d, only represent positive values. We only care about positive times, and we only care about positive distances. So therefore, we only need to look at quadrant 1. Yes, these two equations and these graphs would continue in both directions forever, but the negative values are useless to us in the context of this problem. Next thing, what is the point on the graph where the two equations intersect represent in the context of the problem? So we've kind of already said this, but we haven't explicitly said it, so I want you to write it down using your own words, and then we'll discuss. So pause, write it down, and then we'll discuss. Alright, so the intersection point represents the distance and the time at which the horse catches me. And then the last, this should be pretty easy based on what we just answered in the previous problem. How far did you travel before the horse caught you? And how long was the horse running before it caught you? So that second one's a little bit tricky maybe, or it's not quite as straightforward. You have to think a little bit. But so I want you to answer these two questions. How far did you travel before the horse caught you, and how long was the horse running before it caught you? Pause the video, answer the questions, and then unpause, and I'll talk. Alright, so what do we come up with? Well, hopefully we understand that we ran a distance of 2 kilometers. The horse also ran a distance of 2 kilometers before it caught us. It took the horse 4 minutes to catch us once it started running. So that's why it's really important to make sure we understand the question, how long was the horse running? So not how long total did it take, because we know it took 10 minutes. We found that out earlier. So our distance, which was 2 kilometers, it took the horse 4 minutes. Another way to help understand this is if we go back and look at our graph, we can see that the intersection point is 10:2. The 10 represents time. That's the total time, but remember that's from 0. The horse didn't start until 6 minutes after. So the horse was only running for 4 minutes, but 2 represents the distance. That's the distance that both of us traveled, which was 2 kilometers. We can also get this from back earlier on when we found that there was an intersection point and that intersection point happened at 10 minutes. So the horse caught us in 10 minutes. If we took this 10 minutes here and plugged it back into either of these two equations for t, we could have found our distance value of 2. Okay, so that is systems of equations. It's important that we understand to define variables when we have a model, and then to be able to correctly write our equations from that model. If we can't write our equations, then the rest of the problem becomes very difficult. Make sure that you're always keeping track of units as well. If, for instance, the horse was running in kilometers per hour and we were running in kilometers per minute, we want to make sure that we have the same variables. Or if one of these was in miles and one of them in kilometers, we want to convert one of the variables. So these are all things you have to keep track of when you are modeling.